So as promised, I wanted to go over nucleophilic aromatic substitution. So some electron withdrawing groups, a halide, and a nucleophile instead of an electrophile. What happens with nucleophilic aromatic substitution? A nucleophile replaces a leaving group on the aromatic ring. This is an addition-elimination reaction. Electron withdrawing substituents activate the ring for nucleophilic substitution. Nucleophilic aromatic substitution. We studied electrophilic aromatic substitution in detail in this chapter. In the previous semester year, we had a different book, went over it, and so I'm thinking, man, what if one of these questions shows up on the MCAT? I want to cover it. So what's going on with nucleophilic aromatic substitution? So we have something negatively charged instead of positively charged. That's the most obvious. And it kind of looks like almost like an SN2 event. Here's hydroxide. It hits there, and notice normally we'd have a positive charge that would precess around the ring. Now we have this negative thing. Those electrons can jump there, puts positive charge there, or we take those electrons, put them back down there, then this jumps to there, that can jump to there. So 5 resonance structures. So keeping with our idea of what's a good leaving group, chloride's a good leaving group, very stable base, weak base, and then it leaves. These electrons jump back down, and there we see that we put an OH on the benzene ring. Of course, this is pretty acidic. Take that off if we need. So normally when you see nucleophilic aromatic substitution, you have a good leaving group, and then you have these electron withdrawing groups, and we see these activated positions if we have like a good leaving group there. Chlorine. Nitro groups, ortho and para to the halogens, stabilize the intermediate and the transition state leading to it. Electron withdrawing groups are essential for the reaction to occur. So if you see a hydroxide and some nitro group and a halogen on a ring, that's probably the setup for nucleophilic aromatic substitution. Now, of course, here we don't see any of those, but what we have here is liquid ammonia. And if you just do this for fun, if I take some sodium metal and put it in ammonia, we can have an oxidation reduction reaction occur and end up with, there, I think I balanced it. And you'll recall from our acetylene chemistry, when we added this thing here, that was a strong base. That's how we got this acetylite ion, and then we could do all the interesting things we were able to do with that. The reactant is a halobenzene with no electron withdrawing groups on the ring. We still have our halogen. An alkyl group is actually electron donating. Maybe the thing to look here is, looks maybe like a nucleophile. Use a very strong base like this sodium amide. So what happens? Strong base, pull off a proton, and now look, we have this lone pair here, and we kind of already have this pi structure that leaves, and we essentially form a triple bond. Of course, that looks awfully ring-strained to me. So sodium amide, I didn't enunciate my D last 2 seconds ago. The benzyne intermediate, we have an alkyne, we call it benzyne. Intermediate forms when the bromine is expelled and the electrons on the sp2 orbital adjacent to it overlap with the empty orbital of the carbon that lost the bromide. And this bond angle wants to be 120. It wants to be a linear thing. So these benzynes are very reactive species due to the high strain of the triple bond. And we're in liquid ammonia that pulls off a proton. And so here is our, I would just call it para-aminotoluene, p-toluidide. And here's the same thing in the meta position. Strong electron groups, ortho or para, the addition elimination mechanism is more likely. Without these activating groups, stronger conditions are required, and the benzyne mechanism is likely. All right, any questions on nucleophilic aromatic substitution? On to carboxylic acids. The functional group of carboxylic acids consist of carbonyl carbon with an OH bonded to the same carbon. So possibly from general chemistry, you've already been exposed to all this confusion. There's the acetate ion. There's the acetate ion again. There's the carboxylic acid, which breaks our rule of writing hydrogen on the left. Aliphatic. What does the word aliphatic mean? Means fat-like, aliphatic. So a lot of carboxylic acids have a big, long alkane chain. We say they're fat-like, so aliphatic. An aliphatic chain is typically a big, long chain that's fully saturated with hydrogen. We'll look at unsaturated groups here in a second. Aromatic acids have an aryl group, and you're familiar with our benzoic. So fatty acids, long chain aliphatic acids. Fatty acids, kind of synonyms. Common names. I don't know how common these are, but anyway, they use the Greek alphabet: alpha, beta, gamma, delta, and epsilon, corresponding to A, B, C, D, and E in the alphabet we use. And so this alpha chloral propionic acid, alpha amino butyric acid, two common names. So history just developed and gave us these names. Positions on the substituents on the chain are labeled with Greek letters, starting with the carbon attached to the carboxylic carbon. IUPAC names, much more straightforward. Carbonyl carbon is number 1. We basically name the alkane and chop off E and put oic acid. Of course, here's a methane, 1 carbon. Chop off the E and put oic acid. Any entomologist in here? Any Spanish entomologist? What's the Spanish name for the insect, an ant? I wanted to say what's Spanish for ant, and you'd say tia. Don't have my phone. Almost looks like this word here. So the first guy who discovered formic acid, he took up a bunch of red ants, ground them up in a blender, and put them in a round bottom flask and distilled away. And I guess my phone's taping this. Should have looked that up before I came in here. Formic acid, common name. Acetic acid. So this one's real common. Not too many chemists say, I need some ethanoic acid. They just say, do you have any glacial acetic acid? Need some acetic acid. All right, so let's try and figure this out. I don't like to worry too much about the valeric acid. Who knows that that's based on a 5-carbon chain? Not even chemists. Chemists younger than 60 years old. So if I saw this in class and I was supposed to name it, I'd say 1, 2, 3. I'd take propane, chop off the E and put oic. And then on carbon number 2, I'd say, cyclohexyl. 2-cyclohexyl propane oic acid gets the job done. So now maybe is a good time to learn this substituent. Beginning of the fall, I say, know your alky groups, and we do methyl, ethyl, isopropyl, butyl, tert-butyl, sec-butyl. This isn't an alky group, it's an acyl group. Think back to Fieldcraft acylation, and probably from our chapters on mass spec, you've the acylium ion. There's a couple of resonance structures. Remove the final E from the alkane name and add oic acid. So IUPAC should be fairly straightforward. Which are healthier, saturated fats or unsaturated fats? Pendulum has swung back and forth. Turns out unsaturated fats impart this bond can no longer rotate. These have higher melting points, and I guess the theory is unsaturated fats are more harmful because they can clog your arteries maybe. So we call these unsaturated acids. We'll look at what fat might be. All right, so I'm gonna go 1, 2, 3, 4, 5. Whoops. 1, 2, 3, 4, 5, 6. I'm gonna go hexane, chop off the E and go hexanoic acid. And then here at number 4, I have a methyl. 3 is where the double bond is. And look, we get the stereochemistry. E methyl hex 3 anoic acid. Where do we get cinnamic acid from? You've melted it in lab. Get it from cinnamon. The spice is full of this. That's what gives it its flavor. All right, so here's a twist. They're not telling me this is number 1. Evidently, we're gonna name this carboxylic acid group as a substituent, carboxylic acid. So we just name it as a plain old cyclohexane derivative. Give this priority. So I got 3,3-dimethylcyclohexane carboxylic acid, just like we had cyclohexane carbaldehyde. So same thing as before, chop off E, add oic acid, make carbonyl carbon on the acid group number 1, and stipulate the location of the double bond. And then don't forget about your stereochemistry, E or Z, aromatic acids, named as derivatives of benzoic, so paramethyl-benzoic acid, orthohydroxybenzoic acid, para-amino-benzoic acid, all derivatives of benzoic acid. You can use the prefixes, probably don't count you off with the numbers. If you have more than one substituent. Dicarboxylic acids. I don't like what the book said here. Aliphatic diacids are generally called by their common names, using Greek letters beginning with the carbon next to the carboxylic acid. So have you seen adipic acid before? Yeah, with your cyclohexene lab, you oxidize it away. So when you say adipic acid, you know it's the 6-carbon chain acid on each side. So I guess IUPAC uses these common names. I wasn't satisfied with what the book said. What acid is this? Name this acid. Methanoic acid. IUPAC saved my bacon. Formic acid. Yeah, so when you get a ant bite, a red ant, at least I think of the red ants. Of course, I have been bitten by those little black ones, like when you're out in the garden, you got your flips on, and all of a sudden you feel this burning sensation. There's a gazillion little black ants, but the red ant really just gives you a formic acid burn. I guess methanoic only saved me if I couldn't read. Maybe that's why I got all those weird looks. So here's resonance structure, major and minor. So, if we look at the boiling point of ethanol and compare it to the boiling point of acetic acid, we'll see acetic acid quite a bit higher than ethanol. You form a dimer. So they boil at considerably higher temperature than the corresponding alcohol. Of course, alcohol is a lot more than the ketones. Aldehydes of similar molecular weights. Why do we compare similar molecular weights? What intermolecular force are we holding constant? London dispersion forces. So this is why they're so high. Aliphatic acids with more than 8 carbons are solid at room temperatures. Double bonds, especially cis, lower the melting point. Following acids have 18 carbons, and here are the corresponding melting points. So acetic acid, probably immiscible with water. As that side chain gets longer, it gets longer than 10 carbon atoms. They will not be soluble in water. Very soluble in alcohols, also soluble in relatively non-polar solvents like chloroform, because the hydrogen bonds of the dimer are not disrupted by the non-polar solvent. So some equilibrium here, carboxylic acid reacting with water, conjugate base, conjugate acid, and we write an equilibrium expression. Since there's such a big range, we like to just work in a logarithmic scale and use pKa. It says here the acid will be mostly disassociated if the pH of the solution is higher than the pKa of the acid. Of course, that reminds me of my favorite form of this equation. Let's think about this. Mostly disassociated in this form if the solution has a higher pH. So acetic acid, something kind of like that. So if I'm at a pH of 7, it's got to be now we're doing what we're supposed to. If by whatever means, adding base or whatnot, now we see here, I didn't give myself enough room. We could do the math and figure out the ratio here. And probably maybe tomorrow when we look at a slide on extracting where we exactly want the pH. Turns out 2 pH units away. So a pH of 6.7, probably force it where we want to be to do an acid-base extraction. So everything on this slide you should be able to explain to me from the fall on chapter 2 with our acid-base equilibrium chapter, and perhaps with the alcohol chapter. Here's our alcohol reacting with water. Here's alkoxide, very strong base. Hydronium, of course, equilibrium's way over here. But this one here, equilibrium's still over there on the left. However, we get a lot more of this. pK of 5, pK of 16, definitely a stronger acid. Acetic acid is a stronger acid than ethanol. The question is, why? And we can say, well, the conjugate base is stabilized due to resonance. It can localize the charge. And here we see an energy diagram explaining that to us. All right, that's going to be all for today.